In today's video lesson, we're going to learn about the different gas laws and how they all apply to one another. So first of all, we'll talk about what is an ideal gas. So an ideal gas is one that demonstrates all the criteria of the kinetic molecular theory. So that was when we talked about how no intermolecular forces are acting on gas molecules. When they bump into each other, they don't lose any kinetic energy. And all of those things. So the ideal gas would obey all the gas laws for pressure, temperature, and volume. We'll learn later that not all gases act ideally all the time under certain conditions, but we're always going to assume that our gas is behaving as an ideal gas. So our first law is Boyle's law, and Boyle discovered that pressure and volume, when they're at the same temperature, are inversely related. As the pressure on a gas increases, the volume of the gas will decrease by the same factor. So if you doubled the pressure, the volume would be cut in half. If you doubled the volume, the pressure would be cut in half, and so on. So this example here, we see our gas. We have this volume here. We push the plunger down and compress the gas. The pressure is going to increase by that same factor. So P1 V1 equals P2 V2 is the relationship we can use to calculate the effects of changing one of those variables on the other. We'll take a look at some examples at the end where we combine all of the gas laws together so that we don't have to memorize 3 equations. Instead, we can memorize just one and then keep certain things constant. So in this first example, we can see that as you increase the volume, the pressure decreases, and conversely, as you decrease the volume, the pressure increases exponentially. So if you think about it, when you keep pressing a gas tighter and tighter together, there's going to be more and more pressure acting on that gas. But if you increase the volume, the pressure will expand. This relationship is the inverse of the volume. So if you had 10 milliliters, it would be 1 over 10. If you had 20 milliliters, it would be 1 over 20, and so on. So as the inverse volume increases, the pressure increases as well. So that's it's showing a linear relationship when you plot pressure against 1 over V, so 1 over the volume. This one, if you plot P times V against the pressure or against the volume along, it doesn't matter, either one, you'll see that it's a constant. So that proves that they're inversely related to one another, because as you increase one, the other one's decreasing at the same factor. So with temperature, we so far have been dealing with Celsius temperatures. And the Celsius scale is fine when you're working with water-based solutions, because the Celsius scale is based on water's melting and boiling points, so it makes much more sense to use the Celsius scale. However, the Kelvin scale is much more appropriate for gases because it's calculated It's an absolute scale. We calculate it by adding 273.15. Some places you'll see just 273 to the Celsius temperature. So each Kelvin and each Celsius, they increase by the same factor. But the Kelvin scale is an absolute scale. So if you double the Kelvin temperature, you're doubling the kinetic energy. So it tells us much more about the gas's behavior if we use the Kelvin scale. So if you look at the scale over here, this is our Celsius scale. So 0 Kelvin is equal to negative 273 degrees Celsius. 0 Celsius is 273.15 Kelvin. And then as you increase it, they increase by the same factor. It's just this is much easier for us to understand than this. For us, it's really important for us to know when we're talking about temperature outside where the freezing point is. That's the freezing point of water. And we know that 0 degrees is relatively cold to us. It's a lot easier to factor things that are below freezing and above freezing with the Celsius scale than with the Kelvin scale, because the temperatures that we use in on Earth, they don't fluctuate that much. So using 0 is much more helpful, because if I said it's 273 Kelvin outside, boy, it's really cold, doesn't make a lot of sense. So for air temperature, for regular weather related things, we use Celsius, and when we're dealing with solutions, Celsius makes sense. But for gases, Kelvin makes more sense. A lot of our relationships are based on the Kelvin scale. So Charles' law states that the volume of a gas at constant pressure is directly related to the temperature in Kelvin. So if you double the temperature, you double the volume. So if you had a balloon and it could stretch and shrink easily, if you blew up the balloon indoors at like 20 degrees Celsius, and then you took it outdoors in the winter time to 0 degrees Celsius, it would actually shrink, because the volume is directly related to the temperature. Same thing if you blew the balloon up outside in the cold and then brought it into a warmer area, the balloon would expand. So that's how that works. So our relationship, this one is V1 over T1 equals V2 over T2 to solve these ones. Our third one is Gay-Lussac's law, and that states that constant volume, a gas's pressure, is directly related to its temperature in Kelvin. So P1 over T1 equals P2 over T2. So same thing. If you double the pressure, the temperature would double, and so on. This principle kind of explains why it's dangerous to keep gases under pressure near high heat temperatures. So this is why you can't store your gas canisters right by a heat source, because if you kept the same volume, the gases can't expand. But if you're increasing the temperature, the pressure will also increase. If you've doubled the temperature, the pressure will double, and so on. And that would be quite dangerous for gas containers. They could actually, if the heat gets hot enough, could expand beyond the pressure would be so much that the container couldn't withstand the pressure anymore, and it would explode. So that's why gases explode, like canisters explode if they're in a fire. So all three of those gas laws can be combined into, shockingly, the combined gas law. So it would be P1 V1 over T1 equals P2 V2 over T2. When one value is kept constant, you just eliminate it from the expression. So if we were doing a reaction with the same temperature, then it would be Boyle's law, so it would just be P1 V1 equals P2 V2. If the pressure was staying the same, it would just be V1 over T1 equals V2 over T2, and so on. In our first example, we're told that a helium balloon of 4.5 liters is at standard atmospheric pressure, 101.3 kilopascals. If the pressure on the balloon is increased to 110 kilopascals, what is the final volume? So first of all, we can assume that the temperature is staying the same because there's no mention of temperature. So we have three values here. We have our V1 and P1, and this will be our P2. So we need to find out what V2 is. So remember, P1 times V1 equals P2 times V2. We don't need to include the temperature because it's not a factor here. So we'll rearrange our equation. So V2 is equal to P1 times V1 over P2. So we'll have 101.3 kilopascals times 4.5 liters divided by 110.2 kilopascals. So the kilopascals will cancel out, and we'll get our volume in liters, which is 4.1 liters to round off to sig figs. So our balloon has shrunk to 4.1 liters from 4.5. In our next example, it says Jara is having a party. When she tied her balloons outside, the temperature was -2 degrees Celsius. The pressure was 100.8 kilopascals, and the volume of the balloons was 4.2 liters. A cold front has now moved in, and the temperature is now -25 degrees Celsius, and the pressure is 103.0 kilopascals. What is the new volume of the balloons? So first of all, we're going to have to convert our temperatures to Kelvin. So we add 273. So this one is going to be 271 Kelvin. And the other one will be 248 Kelvin. And then the remainder of the information we can keep the same. So this is going to be our relationship with pressure and temperature and volume. So it's going to be P1 V1 over T1 equals P2 V2 over T2. Now to rearrange this one, it's going to be a little trickier. So we want to know the new volume. So the first thing we have to do is not have things on denominator sides. So this side's going to need to, they're going to need to cross multiply. So we're going to have P1 V1 T2 equals P2 V2 T1. And then we can isolate to get our new volume by dividing both sides by P2 T1. Do the same thing over here, P2 T1. So then these can cancel out so we can know our new volume. So now we'll solve. So V2 is equal to P1, which was 100.8 kilopascals, times V1, which was 4.2 liters, times T2. So that is 248 Kelvin divided by P2, which is 103.0 kilopascals, multiplied by T1, which is 271 Kelvin. So performing that calculation, rounded off to 2 sig figs, we would have 3.8 liters as our new volume. So looking at our third example, we have a tank of chlorine is stored in a concrete room for safety. It can withstand 50 atmospheres before exploding. At 22.3 degrees Celsius, the pressure gauge reads 35 atmospheres. A fire in the building raises the temperature to 87.5 degrees Celsius. What will the pressure gauge now read? So first of all, we should identify our volume. So V1 is 23.2 degrees Celsius. We need to add 273 to make it Kelvin. So that's 296.2 Kelvin. And that's temperature, not volume. Our second temperature is 87.5 degrees plus 273. That's 360.5 Kelvin. So this is not telling us anything about volume, so we can assume that volume is remaining constant because it is in a tank, right? So the volume wouldn't be changing. So it's going to be P1 over T1 equals P2 over T2. But we need to rearrange our formula, so it's going to be P1 T2, because we multiply like so to to make it balanced, and that's equal to P2 times T1. We want to know what the pressure gauge reads, so we want to know what P2 is. So P2 is going to be P1 times T2 over T1. So now we can sub those in. So P2 is equal to the initial pressure, which is 35.0 atmospheres, times the second temperature, so 360.5 Kelvin, divided by 296.2 Kelvin. So we'll solve for that. So our new pressure reading would be 42.6 atmospheres. So while the temperature has gone up, it's still within the safe range. So one thing to be aware of is sometimes you'll have some extra information that won't be used in your equation. So this is how much it can safely withstand. So that wasn't a value that you would use in your equation. That's just to compare. So we can see that here, when the fire raises the temperature, we get a reading of 42.6 atmospheres, but it's still within the safe limits. Our next example says that Kamar drew 25.5 cubic centimeters of oxygen into a syringe at 20 degrees Celsius. He heated the syringe to 65 degrees Celsius. What volume will the gas now occupy, assuming constant pressure? So pressure is not changing. So this one's going to be V1 over T1 equals V2 over T2. Rearranging, we will get V1 T2 equals V2 T1. We want to know what the volume is, so we're going to divide both sides by T1 to get the final volume, and then we can solve for that. But first we need to figure out our Kelvin temperature. So T1 is equal to 20 degrees plus 273 Kelvin, so that's going to be 293 Kelvin. And then our T2 is equal to 65 degrees plus 273. So that's equivalent to 338 Kelvin. So now we'll solve. So V2 is equal to V1 times T2 over T1. So that's equal to, our initial volume was 25.5 centimeters cubed, times our T2, which is 338 Kelvin, and we're going to divide by 293 Kelvin. So we get a volume of 29.4 centimeters cubed.